Hello everyone, this is Sai Rama Varsha from 4th Sem CSE AI department studying in SVCE College. In this session, we will see about quicksort. Our agenda. What is quicksort? Choice of pivot element, quicksort algorithm, time complexity, and advantages. What is quicksort? Quicksort is an sorting algorithm based on divide and conquer algorithm. It picks an element as pivot element, partitions the given array around the picked pivot by placing the pivot in its correct position in the sorted order. Pivot element. There are many choices for choosing pivot element. We can choose either first element as pivot or second element as pivot or any other element as pivot or last element as pivot or middle element as pivot. How does quicksort works? The key process in quicksort is partition. The target of partition is to place the pivot at its correct position in the sorted array and put all the smaller elements to the left of pivot and the greater elements to the pivot to the right of pivot. Partition is done recursively on each side of pivot after pivot is placed in its correct position and finally sorts the array. Now let us go to the algorithm. The name of the algorithm is QSort A of L to R. Here L is the starting position of the array and R is the ending position of array. Input array A of 0 to n minus 1. Output subarray of A of L to R sorted in ascending order. We will check whether L is less than or R and the partition of A of L to R is kept in S. Let us see partition algorithm. The input is A of 0 to n minus 1 and the output is A of L to R. We will consider pivot element as A of L and then I as L plus 1, J as R. We will repeat until A of I is greater than or equal to P. We will increment I by 1. We will decrement j by 1 until a of j is less than or equal to p. Then we will swap a of I and a of j. Until I of I is greater than or equal to j, we will repeat this entire process. If a of I is greater than or equal to j, then we will go to the next step. That is, we will swap a of I and a of j. We will swap a of L and a of j. Then we will return. The return value goes here, S of partition, and then it calls Q sort of A, Q sort of A of S plus 1 to R, and Q sort of A of L to S minus 1. This is how algorithm works. To understand better, let us see with an example. Here, the size of array is 5 and we have 4, 7, 2, 1, 8 are the elements of the array. 0, 1, 2, 3, 4 are indexes of the array. According to algorithm, let us take the pivot element of A of L. L is 0. A of 0 is 4. So our pivot element is 4. I is L plus 1. 0 plus 1, that is 1. J is R. R is nothing but the last element, that is the position of last element, that is 4. Now we will check with the condition whether A of I is less than P or not. A of I, A of 1, that is 7, is less than pivot. Pivot is 4. 7 less than pivot, 4. No, it is not true. So I remains same and the I value is 1. Now let us go to the J part. A of J is greater than pivot. A of J is 8. 8 is greater than pivot, 4. That is true. Now J is incremented to 3. Now let us check A of 3 is greater than pivot or not. A of 3 is 1. 1 is not greater than 4. So J remains same. Now I is equals to 1. J is equals to 3. Now we will swap A of I and A of J. That is 1 and 7 get swapped. Now again we should check whether I is greater than or equal to j or not. I is 1, j is 3. 1 is not greater than or equal to 3. So again we have to repeat the same step. Again we have to check a of I is less than pivot element. 1 is less than 4. Yes, it's true. So I is incremented to 2. Next, 2 is less than 4. So I is incremented to 3. And next, we will check with 7 less than 4. It's not true. So we will go to the j part. A of j greater than p. 7 is greater than 4. It's true. So j will be incremented to 2. Now, 2 is greater than 4. It's false. So j remains as 2. Now, I is equals to 3. J is equals to 2. Now, we will swap. After swapping, we will get this array. Now, I is equals to 3. J is equals to 2. Again, we will swap A of I and J. See, we swapped A of I and J. Now again, we will swap A of L and A of J. That is 4 and 2. Now, our j value is 2. We will return it to S. Now, we will return it to S. Now, we will consider the array. Sub-arrays we will consider. L. L is 0. S minus 1. S is here which we return the j value 2. So, S is 2. 2 minus 1 is 1. So, A of 0 to 1 is our sub-array. A of 0 to 1 is nothing but 2 and 1. Here the pivot element is 2 and L is 0, R is 1. L is nothing, I is nothing but L plus 1. That is 0 plus 1, 1. J is nothing but R. J is equals to 1. 1 less than 2, true. So I will become 2. Now 1 greater than 2, false. So J will become 1. Swap of A of I and A of J is not possible because in I is equals to 2 we don't have any element. So swapping of A of I and A of J is not possible. So, now A of I is greater than J. What is I? What is I? 2. 2 is greater than 1. Yeah, it is true. So we will swap. Swap A of L and A of J. Now we will swap. Now return J. What is our J? Our J is 1. So check whether we can further divide this into subarray or not. See, if S is 2, 0 to S minus 1, that is 0 to 1 minus 1, it's not possible. So we are not dividing this into subarray. Next, second subarray, S plus 1. What is our S? S is 1. 1 S is 2. S is 2 before in previous here. S is 2. So S plus 1. S plus 1 is 3 and R is 4. Now our pivot element is 7. I is L plus 1 and J is 4. Again we'll check with the condition whether A of I is less than P. 8 is less than 7. It is false. So I will become 4 itself. If A of J is greater than P, 8 is greater than 7. It is true. So J is 3. 7 greater than 7. It is false. So J will be 3 itself. Now I is 4, J is 3. We can swap A of I and A of J. Again, check whether I is greater than J or not. Yes, I is greater than J. So again we will swap. Now swap of A of I and A of J, but L is equals to 3, J is equals to 3. No swap possible. So we will return J is equals to 3. Now to divide this array into subarray, it is not possible. So our sorted array is 1, 2, 4, 7, 8. This is how we represent the above algorithm in a flow chart. Let us see the time complexity of algorithm. The best case complexity. In quicksort, best case occurs when pivot element is in middle or near to middle. The best time complexity of quicksort is n log n. Average case. It occurs when the array elements are in jumbled order, that is not properly ascending and not properly descending. The average time complexity of quicksort is n log n. Worst case complexity. In quicksort, worst case occurs when pivot element is either greatest or smallest element. Suppose if pivot element is always the last element of array, the worst case would occur when the given array is sorted already in ascending or descending order. The worst case time complexity of quicksort is n square. Let us see the advantages of quicksort. Quicksort works rapidly and effectively. It has the best time complexity when compared to other sorting algorithms. Quicksort has a space complexity of log n, making it an excellent choice for situations when space is limited. Thank you.